In this video, we're going to take a look at how we can apply the concept of integration to some applications in physics. And we're going to look at two in particular. The first one that I want to talk about relates to fluids, and it's what's kind of called typically called a statics problem, so nothing is moving. But we're going to be talking about basically pressure and fluid force in this first example. All right, so application one, pressure and fluid force. The force of a fluid will increase with depth. And what I mean by that is if you have basically, if you start to submerge something underwater, the force, the pressure, which is related to force, pressure is force per area, will grow the deeper that you go. Right? This is why there's limitations to how deep a submarine can go before it gets crushed. So this is the idea. It turns out that that force and the pressure, which is force divided by area, it increases depth and it increases linearly with depth in the following way. So the force and pressure, which is force per area, of a fluid so that force of a fluid on an object, so it has to have something to be acting on, so the force that is exerted on that object increases with depth. And this is hopefully a fairly intuitive idea. If you've ever gone swimming and dived down in the deep end, you'll notice you can often feel it in your ears. It starts to become very uncomfortable if you go down more than, just a few feet below the surface of the water. One way to kind of think about this is you can think of the water above something as sort of a big mass that's sitting on top of an object exerting a force down on it. So how much mass sitting on an object? And so if I draw a picture here and we have a region under the water that I'm going to draw with it's just sort of a little rectangular region. Right, so here's some region A, and above it we have sort of a box almost that you can think of the water kind of sitting up here. Depending on how deep we go under the water, which is going to be this variable d here, we will have more and more water sitting on top, right? So if we preserve A as sort of a constant area, but we increase depth, then the amount of water that's sitting on top of A obviously increases. And we can figure out how much force this water is exerting by using, so how much mass is sitting on the object, and then how much force. So we can figure it out by using our standard equations. In this case, the force is going to be the mass times gravity. So if we can figure out what the mass is, and we know the gravitational constant is 9.8 meters per second squared, or 32 feet per second squared, however you want to approximate that, then all we need to do is figure out this mass. And this mass is going to be equal to the density of our fluid, which we're going to use the letter rho for, the Greek letter rho, times the volume. And so these are the letters that we're going to use. Rho is our density, V, capital V for volume. And that volume, looking at our picture, if we just say, let's pretend that I just drew these as little waves so it looked like a fluid. But let's assume it's a nice flat surface. That volume is just going to be basically a big cube or a rectangular prism. And it's just going to be the area of the base times the depth. So the volume is just simply D times A. And in fact, I'm going to write them in the other order so we don't get confused and think it's like a differential. So A times D. Okay, so when we put this expression in and substitute that into the V here, and then we take this expression and substitute it in for the M here, we get that this force is equal to rho G A D. And this is what's called the hydrostatic force. This is the force that is simply due to all this water pushing down on this plate. You could think of this plate with area A, that force due to gravity. The pressure, so if we want to talk about pressure instead, we need to recall that up here I said that pressure is defined as force per area. So we need to take this force and divide out an area, which luckily it shows up right here as an A. So we need to divide out the area. And if we just want the pressure, again, it's force over area. So in our case, that force was rho GAD. We're dividing by that same area. Right? The total force is distributed over this entire area. And so at any given point, we can think about the pressure. We can cancel these A's. And the pressure is just going to be rho GD. So it's linearly proportional to the depth. So this is the hydrostatic pressure. And when I say linearly proportional to the depth, I simply mean that the way that it relates to the depth d here is as a linear function, right? This thing isn't squared or cubed or square rooted or anything like that. It's a linear function. So this is the hydrostatic pressure. If we look at the units of these things, typically what we'll use for force, right, because it's a force, this would be in maybe newtons up here. And the hydrostatic pressure will be in newtons per meter squared. Right, we've got to divide out by that area. So that's the units of these things. So one thing that is slightly less intuitive than this, because this is pretty easy to show, right? We just kind of literally looked at a picture that showed this volume of water pressing down on this this plate, this region with an area of A, and this all kind of followed from that with just relatively basic understandings that mass is going to be the density times the volume, and the volume is going to be the area of the base times the height. These were relatively basic mathematical ideas. But one other important thing to note, and again, this is less intuitive, is that pressure is felt in all directions. It's not just felt from above. So what I mean by this is, imagine that you're swimming and you dive down under the water. As you go under the water, you don't feel more pressure on your back that's facing up towards the surface of the water than on your stomach that's facing down towards the bottom. The water's basically pressing in on you from all directions. And so if you go under the water and you kind of do a rotation under the water, you won't feel like the pressure only on the top side of you as you spin around. you won't feel anything if you spin around under the water because the pressure is going to stay uniformly pressing from all directions. So you can do this, with your ears. You go under with your head, and with your head facing forward so that your ears are out to the side, you feel that pressure in your ears. If you suddenly turn your head so that your ear is pointing up towards the surface, you feel the exact same amount of pressure. So this is kind of an interesting idea. The pressure is typically uniform from all directions. And this same thing on a submarine. When a submarine is under the water, the pressure is pushing in from all directions. It's not like getting a leak on the top of your submarine is somehow worse than getting a leak on the bottom side of your submarine. If you get a leak anywhere on the submarine, you're going to have water spraying in through that leak when the submarine's 500 meters under the surface of the water. So this is the idea. Pressure comes uniformly from all directions. So this means that the pressure in the vertical direction and horizontal direction are the same. Oops. Or think of it this way, and this is in fact kind of some examples we're going to do in a minute. If you've got a fish tank, just because the walls of your fish tank are vertical doesn't mean that so when I say they're vertical, that means there's no water above, quote unquote, above the wall, pushing down on it. But there's still absolutely pressure from the inside of the tank pushing outward on the walls. So this is the exact same idea that I'm trying to talk about. If you drill a hole in the side of your fish tank, even though there's no water above that hole pressing straight directly down on the hole, water's still going to shoot out the side of that fish tank because the pressure is uniform and it pushes evenly in all directions. So that is another good way to think about the point that I'm trying to get across here. Okay, so one of the things that we're going to be doing is finding the total hydrostatic force exerted on basically like a vertical plane that's submerged in water. Literally something just like the side of a fish tank or a dam that's holding up a lake, something like that. So we can find the total the total force, hydrostatic force, total hydrostatic force, I'll just write force, on a vertical plane as follows. So that force, all I'm going to do is basically come back to the equation that we just had right here, right? I know that pressure is equal to the force divided by the area. We have this property here about the pressure. The pressure is felt evenly in all directions. So I'm going to just go back and rearrange this formula to solve for force instead of for pressure. So if I multiply both sides by area, I'll get pressure times area is equal to the force. Both of these are possible that they can vary by depth. So these may vary with depth. Obviously, the pressure is going to vary with depth. The deeper down you go, the greater the pressure. But the area may be the same too. If I have something that's totally uniform, if this is the wall, the vertical plate that I'm looking at, then it's not varying with depth, right? This little bit of area down here looks the same as this bit of area up here at the top. But if we have a dam or something that has a shape like this, where it's narrower at the bottom, wider at the top, right, the area down here is different from the area up here. So this is what I mean by the area in this case. So over here we had area is constant, but over here we're going to have area that's a function of depth. It's a function of the y direction. Tinier area at the bottom, larger area at the top. And obviously pressure is going to be a function of y, the depth. So this is what I mean. And if we want to find the total force, all we're going to do is basically slice this up and find the force on each one of these little sections. So I'm just going to use this formula over here. What's the pressure on this little piece? Multiply it by the area of this little piece. What's the pressure on this piece? Multiplied by the area. Pressure on this piece multiplied by the area. And add them all up. Take the limit as the number of slices goes to infinity and the size of each slice goes to 0. The area of each slice goes to 0. And we have our integral. So in this case, if we want to find the total, what we'll do is sum from I equals 1 to n. Maybe this is 1, 2, dot, 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 up to n at the top of the pressure at that given point, so at the depth yi, times the area at that depth yi. And for us, I'm going to use this little, the way we're slicing it up, this is going to be my little dy, or delta y, however you want to write it. You can write it as delta y for now. But that's my small parameter. And I'm going to use the distance across, I'm going to call it the length. This is what our book uses. They use L. So L sub yi. So this formula, the area, is just going to be that cross-sectional length times our little small parameter, which is our delta y. So we're treating all of these as a bunch of little tiny rectangles. That's all we're doing. And the pressure, we have our formula from up here. Where is it? There we go. The pressure is the density times the gravitational constant times d, where d is the depth of the water. So that is going to be the part that varies with y. Depending on where we put our origin, the depth of the water may be y if we put the origin up here. But if we put the origin down here, it'll be some function that still depends on y in a linear manner. So this is going to be rho g times some depth of that slice, y sub I. So those are the two pieces that go into this. So if we put these together and pull out the constants, so the things that are constants are the rho and the g. We're assuming the fluid we're using has a constant density, which is a fairly good approximation. And most times we're assuming g is our gravitational constant. And we will have our sum from I equals 1 to n of d sub yi times L of yi delta y. Then we will take the limit as n goes to infinity, and our delta y correspondingly goes to 0 because our delta y is just going to be the total height here divided by n. Same way that we've always done it. And we get that our force is now going to be an exact representation. So I'll have my rho and my g out front. We're going to integrate from the bottom to the top. I'll call it C and D. So maybe C is down here. D is the height up there. Hopefully it's not too confusing. Maybe I should pick different letters. But normally we use C and D when we're integrating with respect to y, which is what we're going to be doing here. But this D, just to be totally clear, this D is different than this D. So maybe I'll pick a different letter. Maybe that is not a good letter to use. I don't know. We'll just call them A and B again. I think our book uses C and D still. So, well, whatever. I'll just assume you guys can keep track of that. C and D. Let me go back and just stick with C and D. And our depth is going to be some, again, function of y. And our cross-sectional length is going to be some function of y, dy. So, again, d of y is the depth of the fluid at y, and L is the length, so the cross length, L of y, I should say. L of y is the length of the plate that we're looking at, or the dam, or whatever it is. So I'm using the word plate to refer to whatever this, be it the side of an aquarium or a dam or whatever, literally just a plate that we submerge under the water, whatever the case may be. Okay, the side of a submarine, whatever the case may be. Okie doke. So, if we do some examples, we can see that this is a relatively straightforward type of problem. I want to do a tank, and this maybe has sides that are 5 feet tall and 4 feet wide. Is filled with water. And you know what? Let's make our life easy and not use feet. Let's call it meters so that I can use easier constants on this one. So 5 meters by 4 meters is filled with water. We want to find the total fluid force on one side of this tank. Force on one side of the tank. So basically what I'm suggesting is the side of our tank. I guess I should draw it semi to actual proportions. So it should be deeper than it is tall because that's how I set it up. So let me erase this a little bit. Okay, so here's my rectangular tank. This dimension is 4 meters. And this, maybe we're interested in finding the pressure or the force on one little slice of our tank right here at the position, here's our position y. The thickness of that is going to be our little small parameter dy. And we can decide where we want to put our origin. I'm going to put the origin up here at the top. So this is what I'm going to call 0. And I'm going to have the positive y direction go downward. So down here at this point, that's going to be 5 meters down at the bottom. So let me give myself a little more room to draw this out. Right there. That is my 5 meters. And that means the distance from the top down to this point, that's my d of y, the depth that I'm interested in. Again, we could have put the origin down at the bottom and had y go upward, and the depth would just be 5 minus whatever the y value is. It's totally your choice, whatever one is more intuitive to you. So our force in this case is going to just be rho g times the integral of, we've got to do the entire side of the tank. So it's going from a depth of 0 down to a depth of 5 meters. And now we've got to multiply, let's get it all on the screen here. We've got to multiply our depth function times our cross-sectional length function. And our depth is just literally going to be, because we put the origin here and the point that we're interested in down here, y, the distance between 0 and y is our depth. So it's just y. It's literally y minus 0. So our depth, our d of y, is simply y in this case. If we were doing it with our origin down here, then our depth, the distance from the top down to that particular y value, would be 5 minus y. But we'd wind up with the exact same result at the end of the day. And our cross-sectional length here across is 4 meters, so that's just a constant. We've got our dy. That's it. So this is going to be a really easy one to integrate. We can pull that 4 out. So I've got my 4 rho g integral from 0 to 5 of y dy. When we do that integral, again, I'll have my 4 rho g. I'm going to get 1/2 y squared, and we're evaluating that between 0 and 5. And right off the bat, if we want, we can cancel out the 4 and the 1/2 and just get a factor of 2 when it's all said and done. And we will get 2 rho g times 25 at the top, and at the bottom 0. When we plug in those bounds of integration, so we get 50 rho g, and now we just need to know what fluid it's full of, assuming that it's filled with water, as we've stated here. The density of water is a nice round number. It's 1,000 kilograms per cubic meter. So rho is 1,000 kilograms per meter cubed. Gravitational constant, close enough, 9.8 meters per second squared. So we can plug those two values in and write this however you want. You can leave it as whatever, 50,000 times 9.8. And again, when we take into account all of the units of everything that we've gone through all across the way here, this depth is going to have a length, this has units of length, this thing has units of length, these all wind up having units of our volume. We've got this other rho and g out here, and when we multiply all the units together, we get units of force. So it has newtons. You can actually do this multiplication if you want. What do we get? Like 400 and... Should probably not trust myself to do that in my head. Am I doing that right? So 0.2... No, definitely not correct. Wrong. 490? Yes. There we go. One of those days. So 490,000 newtons of force. And this gives you some sense of why, when you see the total force being exerted on this this piece here, this is, the proportions that we're looking at, 5 meters by 4 meters. This is the type of a side of a tank at like an aquarium or something like that. And so you can understand why the glass at aquariums is so thick if it's got to withhold this kind of force. So just keep that type of thing in mind. So this one was easy though, because our cross-sectional length was a constant. It was just a rectangle, so it was always 4 meters across. What happens if we do something that isn't a uniform shape like that? So let's do a shape like the one that I talked about earlier, where it's a dam. So let's say a dam, and in this case we'll do one with feet. So a dam is, and we're just going to have uglier constants, 100 feet tall with a width of maybe 90 feet at the top. And maybe by the time you get down to the bottom, it's down to only 70 feet. What is the total force on the dam? It's the total hydrostatic force on the dam, assuming it's all the way full. So we're going to assume that the water's literally all the way up to the top of the dam. Okay. Again, because we're using feet, the process isn't going to change. It's just we're not going to get to use 9.8 meters per second squared and 1,000 kilograms per meter cubed for our constants. Instead, we're going to have to use the ones in our imperial units, and they're just uglier numbers, but we'll deal with that in a minute. Let's start with a picture. So here is let's say the dam looks something like this. So again, 90 feet across at the top, 70 feet across at the bottom. This vertical distance is 100 feet. And we can figure out where we want to put the origin. Again, we could put it at the bottom, we could put it at the top. In this case, let's put it back at the top again. And so I'm going to have, oops, that's fine. Let me erase this. Again, the positive y direction is going to be down, and this distance right here is what I'm calling my 100 feet, down to that mark. So again, what I want to do is take a little slice of the dam and figure out what is the force exerted by this one little slice. There's a couple of different ways we can do this. But really, we just need, the hard part is going to be figuring out what is this distance L of y? How does this horizontal distance across vary with the depth y? And so again, this is our depth y right here. So again, our depth is going to be easy. It's just going to be y. It's 0 at the top is our depth, and by the time you get down to y equals 100, we're at the bottom of the dam. So the depth d of y is just going to be y. So hopefully that's obvious. D of y is just simply equal to y. But L of y, this length, is a little bit trickier. So how are we going to figure it out? There's a couple of ways we can do it. I think the easiest one is to basically think of this thing as, oops, let's not delete the whole drawing. So I want to kind of slice a triangular side off here, plus same thing on the other side. Slice it off like this. We have a central portion that is uniformly 70 feet across. And then we have this triangular portion that we're going to have to add a depth that's going to be proportional. We can use similar triangles to figure this part out. So what is this distance right here? Well, if we chopped out the middle 70 feet and the top was 90 feet, that leaves 10 feet on either side. So we'd have the 70 in the middle, plus, if assuming this is a nice symmetric dam, to get up to the 90, we'd have the remaining portion, which is 20 additional feet, split evenly amongst the two sides. So I'm going to call that 10 feet, and similarly over here, here's the other 10 feet. And so we know the depth, which is 100 feet, so I know the length of this side, I have this side, and now we can use similar triangles. I draw the triangle I'm talking about over here. So this is 10, this is 100, and we have something right here where this depth, let's call the whole thing 100, and this depth is our depth y, right here at that point. So if I want to figure out this distance, that distance is going to be 100 minus y. Right, because it's the distance from y, which is measured here being 0, again the origin's at the top, so 0 down to y. What distance is left over? Well, if the whole thing's 100 feet deep, this remaining distance must be 100 minus y. And here is this little extra bit, we can call it A in both pieces, and we're going to have basically the total cross-sectional length is going to be 70 feet plus 2 of these little pieces of A. So we just need to figure out what A is. And using our similar triangles, I know that 10 is to 100. So the cross distance here, the horizontal distance here to the vertical distance, as A is to this distance, which is 100 minus y. And we can multiply both sides to find out, or cross multiply, or however you want to do it. Multiply both sides by 100 minus y to get, so this one is just going to be simplified to 1/10, and we'll just get 100 minus y over 10 when it's all said and done. So I just need to add 2 of those to 70. So my total length is going to be the 70 plus 2 of these a's. So 70 plus 2 times 100 minus y over 10. So there's my L. And now we can put everything together, and we get the following. Our total force on this dam is going to be rho g, and we'll come back to what that is in just a minute, times the integral from 0 to 100. I want the full depth. Again, we said we were assuming the water's all the way up at the top, so the depth of the water goes from 0 all the way down to 100 feet. And our depth, our d of y, was just y. And our L of y, the cross-sectional length here at any given point, is going to be 70 plus, I can simplify this a little bit, the 2 and the 10 will cancel, and we can write this as basically just 70 plus 100 minus y over 5 instead. dy. Okie doke. So we're looking at that. We can, again, clean this up with a little bit of just algebra before we jump into things. Rho g integral from 0 to 100. And I'll have y times, if I break this fraction up into two separate parts, I'm going to have 70 plus 100 divided by 5, which is 20, minus y over 5. And so these are just going to give me a 90, and I have fewer terms now to deal with when I integrate. I'd rather do the algebra ahead of time and save myself some trouble with integration here. So I've got y times 90 minus y over 5 is a cleaned up version of that. And we can again distribute through. So we'll have rho g integral from 0 to 100 of 90y minus y squared over 5 dy. And we'll integrate that, and I'll get 90 y squared over 2 minus, we've got this 1/5 out in front, and that y squared will become a 1/3 y cubed. We're evaluating that between 0 and 100. And we get to plug these numbers in and come back to this rho g at the very end. So let me not bother with that for now. But over here I'm going to have 90. 100 squared is, what, 10,000? Is that right? Yeah. So 10,000 divided by 2 is going to be 5,000 times 90. It's going to give me 450,000. Let's just do this on a calculator instead of trying to not having one of those days today. All right, 10,000, 2 times 90, yes, 450,000 from that piece. Over here, we're going to get 1/15 of 100 cubed. 100 cubed, it should be a million. And we're taking a 15th of that, which is 66,666.6 repeating. And that is the whole thing evaluated at the top. When we evaluate it at the bottom, we'll get no contribution whatsoever. And so I'm going to have rho g times this difference, which is 383,333.3 repeating. And lastly, the rho and the g. So we need the density of water and the gravitational constant, both of them in feet, in imperial units. I'm just going to give us what this constant works out to, and you can just feel free to plug in this constant if you remember it. this rho g winds up being 62.5. Once we multiply the density of water per cubic foot, so basically the mass per cubic foot, times the gravitational constant, which is like 32.2 feet per second squared-ish. And we get rho g being equal to, this is units of pounds per cubic foot, I believe. That's what we wind up with. No, is that right? Yeah, pounds per cubic foot. Or this is a mass, or not mass pounds, this is a force pounds. So I think that's what we're good with right there. And then we multiply it by this, which wound up being our volume. And the whole final number we get when we do that multiplication is, let's see here, 23,958,333.3 pounds of force is what I wound up getting. Right, this had units of basically volume. This was cubic feet. Which makes sense, right? A little tiny length, a depth, and the cross-sectional length. So these things here make up a volume. We're just adding up a bunch of little tiny volumes. Okay, so here is our answer in that case. The hardest part in these problems, other than just the arithmetic at the end, basically, is making sure that you get a good expression for this function here, the cross-sectional length, on a problem like this. So that's our first application with a couple of examples. That's our pressure and fluid force. There's some other examples in this section. I really only want to do one more. And this is something that you'll probably see again, typically in Calc 3, or if you go on and take a vector analysis course at like UNM or at another university after this, you will probably encounter some of these ideas again. And this is what's called a centroid, which in plain English is usually what we refer to as the center of mass. So how do you find the center of mass of an object? And in this case, it'll be a planar object for us. So you can think of approximate it with like a sheet of something with no thickness. So basically, the center of mass slash centroid slash, it's also sometimes called the center of gravity, is basically sort of our balancing point. So if I draw, here's some region, and let's assume that it's really, really thin, because you'll do this in Calc 3 and you'll basically learn how to do it for fully three-dimensional objects, but for us, we're basically treating it as a 2D object. So this thickness is basically vanishing. We'll be able to find kind of the point on which this thing would balance. So if you sort of put something right there, this point P is point where our plate balances. And this is the centroid slash center of mass slash center of gravity. And there's actually some kind of cool things you can do with stuff related to this. There's something called a center of curvature, a center of buoyancy, that have to do with sort of the shape of an object and or the point at which sort of basically where the center of buoyancy has to do with like an object that's submerged in water and is floating. And you can relate a bunch of these topics. This is something, hopefully you'll do a cool example of this in Calculus 3 or in a vector analysis class somewhere down the line. But you can talk about the ideas of stability of objects. Obviously, hopefully this kind of makes sense. Center of mass should in some way relate to the stability of some object. If you tip the center of mass out over past the edge of the object, right? If you tip a chair over that has a couple of legs like this or whatever, right? Here's our chair. And if we tip it over so that the center of mass gets beyond, gets beyond the pivot point here, so if you tilted it back so that the chair is leaning back, hopefully this kind of makes sense, and our center of mass, which is over here, is now like directly above this point, it would basically be balancing, where this is the, again, the point P, the center of mass, and this is sort of our pivot point down here. And if we were to tip it any further back, if this point P moved any further to the left, so that it was not straight above this, but in fact to the left of this point, the whole thing would tip over. And so this is one of the cool applications you can talk about. They use this in, these ideas are sort of fundamental to robotics and a ton of other interesting applications like that, is basically figuring out where is the center of mass and how does that center of mass relate to other important points on the object, maybe where it's making contact with the ground and pivoting around, things like that. So let me delete this. We don't need this picture, but that's the reason we might care about the center of mass. It also, similarly, if you're doing something in space, if you're sending an object up into space, the center of mass or center of gravity is the point about which it would rotate if it was sort of free floating without gravity being applied to it. Okay, so this discussion, the idea of a centroid or a center of mass, is easier if we, instead of starting off with a plate like this, is if we instead of think of a scale and we're just trying to balance basically 2 points on the scale. So let's start by instead balancing 2 points, point masses we'll call them. We'll call them M1 and M2. When I say a point mass, all I mean is all of the mass of this object is concentrated at a single point. So it's sort of a hypothetical version, doesn't exist in real life, but it makes this discussion a little bit easier. You can think of it as basically just 2 people sitting on a teeter-totter, and the teeter-totter itself is massless. That's kind of how we want to think about it. We want to find a point where these 2 things balance each other, where the downward force due to gravity is the same on either side of this pivot point. So let me draw a picture first, and hopefully it'll make it more clear. So I'm going to draw a number line here. Ooh. Try to draw a number line here. And I'm going to put the origin over here and say here is the first location. I'm going to call it x1, and this is right where our point or first mass is sitting. And then if we go further down this to some other point, x2, this is where our second mass is sitting. And so the balancing point is going to be somewhere in between these 2, and we can have a little intuition for where it's going to fall, right? It has to be in between them. It can't be outside of them. So hopefully that is intuitive, right? You can't have 2 people sit on the same side of a teeter-totter and somehow have it magically balance. The pivot point has to be between the 2 people on our teeter-totter. And depending on which one of these 2 people is heavier, that'll give us some indication, right? If I sit on the teeter-totter with my daughter on opposite sides and the pivot point's right in the middle, if I'm the heavy one, I'm M1 over here, and she's the lighter one, M2 over here, I'm going to go down. We're not going to be balanced. And to make up for that, if I want to play on the teeter-totter with my daughter in a way that we do both balance, I can make up for that by moving myself towards the center. And another way of thinking about that, it would be moving the center, the pivot point, towards me. And so if this is heavier, we would expect the pivot point to be closer to this side. And this pivot point is what we're looking for. It's what we're going to call x bar. This is the center of mass. And you want to think about it as basically gravity is pulling down on both of these, and this is the balancing point, right? And if M1 is heavier, this center of mass is going to be closer to that side. So it's not just how heavy the 2 things are, it's also how far each one of those is from the center of mass, from that balancing point. It turns out the way that you actually conceptualize this is with something called the first moments. So this is the point. The center of mass, or the centroid, is where the first moments balance. And exactly as I said, the first moment is going to take into account both the mass and the distance from this point here. So the first moment, and the reason it's called the first moment is because there's also something called a second moment and things beyond that. And these are, again, important physics concepts that you'll learn more about in a physics class. We're just giving you sort of an introduction here. But the first moment is simply mass times this distance, where the distance is the distance between the point and the sort of center of mass, if you want to think about it. In this case, what we're going for is we want m1 times, I'll call this one d1 and this other one d2. I want m1 d1 to be equal to m2 d2. These are the first moments. This is the first moment of this point. This is the first moment of this point. And we're looking for the point where they are equal. When equal, we've found the centroid, or center of mass. Center of mass. Abbreviate it that way, so I don't have to keep writing this out. Okay, so let's think about this in terms of the picture that we've got here. I can write this distance. If we're calling this point x bar, that's the center of mass that we're searching for. It's what we're trying to solve for. I can think of this distance right here as being x bar minus x1. That's what this d1 is. So what we really have is that first mass times x bar minus x1. That is our d1 distance, the distance from this point to this point. So from x bar to x1, to keep it a positive number, we'll do x bar minus x1 on our number line. And over here, this second distance is going to be x2 minus x bar, also to keep it positive. So I want that to balance with m2 times the second distance, d2. So this is this piece. d2 is going to be x2 minus x bar. So that is that piece over there. And now we can just try to solve for x bar in this equation. So if we can solve for x bar, we're good to go. X bar is our center of mass. And so I'll distribute through, collect like terms. So we'll have m1 x bar minus m1 x1 is equal to m2 x2 minus m2 x bar. All I've done is distribute the masses through. Let's collect the two that involve x bars, both on the same side, and the ones that involve the other terms, put them off on the other side. So I'm going to get out of this, let's move the x bars over to the left. So I'll have m1 x bar, and I'll have to add that other one, so plus m2 x bar. And when I move over to the other stuff over to the right, we already have the m2 x2 sitting over here, but I need to move this term over here by adding it to both sides. So I'll have plus m1 x1. And now we can factor out that x bar, and it's going to be x bar times m1 plus m2 equals this whole mess, m2 x2 plus m1 x1. And the last step is to simply divide by those two masses to solve for x bar. So I've got m2 x2 plus m1 x1 divided by m1 plus m2. And if you look at what we wind up with, these things on the top, this is simply the sum of the first moments. Right? The first moments we defined as being simply in this case, a mass times a distance. And so we can call, if we think of like x1, the units of these are going to be basically distances. They have units that are the same as of the first moments. So these are the first moments of the two point masses relative to the origin over here, right? Because x1 is the distance from the origin, x2 is the distance from the origin to these two respective points. So we're adding up all the moments relative to the origin, right? So just make that totally clear, relative to the origin. And down here, it's simply the sum of all the masses. And it turns out we can generalize this to more than 2 points, right? What if we have more than 2 people sitting on our teeter-totter? What if we add more and more and more? And eventually, what if we add an infinite number of these point masses so that instead of just having individual discrete points in space, we have a solid object that we're wanting to find the center of mass of. So we can generalize this by adding more and more point masses until we essentially have a solid object. Right, so basically take all our individual points, let the number of points go to infinity, and we can treat it as an actual region. So our x bar is going to be the sum now, right? We're summing 2 things. So on top it's going to be this, so it's the sum from I equals 1 to n, and we'll eventually let n go to infinity. On top we have all the m sub I, x sub i's, right? There's all the first moments, and on the bottom we're just summing up all the masses. So all the m sub i's. This thing on the bottom is eventually just going to be the total mass of our object. So if we let n go to infinity, we wind up getting that x bar is equal to, so we're essentially taking the limit. On the bottom, we're just going to have the total mass. So assuming we know the mass of our object, of our plate, of our region that we're interested in, and we know that it's equal to m, I'm just going to write this as 1 over m, and we've taken care of the denominator. The remaining part is going to be basically the sum of all of these moments, but after we've taken our limit as n goes to infinity, this is now an integral, so we're integrating over the region of basically our xi, which is just going to be x times the mass. And the mass is going to be, let's just write it in words for now. So this is our x sub I. Excuse me, I had to sneeze. Sorry, so this is our x sub I term. What am I looking at? This was our x. This is this part. And our mass, how do we find the mass of an object to begin with? Well, we found it over here. The mass is just going to be the area of this region, because it's a 2-dimensional region, times its density. So this is just going to be rho times the area of that region. But how do we find the area of a region? So if this is our region over here, we have y equals f of x and y, and here's our region, a to b. How do I find the area of this? By simply integrating f of x minus 0. And we can generalize this if we had a different curve on the bottom, doing something like this. If we had some y equals g of x, we could figure this out as well, but I'm going to stick to the simple case where the bottom is 0. We'll just stick to that. So this whole thing becomes 1 over mass times the integral from a to b of x times rho, which we're typically going to assume is a constant. For all the examples we're interested in, we'll assume uniform density, times the basically f of x. because we're integrating f of x dx to get the total area here. So this is kind of the idea. This is what this all looks like. This is going to be uniform. And it turns out if it's uniform, we're going to be able to, this mass over here is also rho times area. And we can basically cancel the rho here and the rho here, if you want to think of it that way. And so what we wind up with is we had the density inside and the density outside, but assuming it's a uniform density, we can pull this outside and cancel it with this one that's in the denominator over here, because basically the mass showed up in two places. The density showed up in two places. And we wind up with x bar is equal to 1 over the area times the integral from a to b of simply x f of x dx. That is how we find the center of mass in the x direction in this case. Incidentally, you may see this thing referred to as m sub y. It is a moment, and it's basically with respect to the y-axis in a sense, because at the y-axis, that's where our origin was, so to speak. So it's basically how far are all these points from relative to the y-axis. So you may see this if you read the book. Just know that that's all this refers to. It's the moment with respect to y. But you need the moment with respect to y to find x bar, because the moment with respect to y takes into account distances from the y-axis. That's what this notation indicates. So this is the formula. If we had this g of x down here, you would simply do f of x minus g of x. I'm not going to worry about an example like that. I won't give you an example like that on any quizzes or exams. If this shows up anywhere, it'll show up as a simple one like this. You'll do those more difficult ones down the line in a later class. Similarly, we can get the one for y bar. So all I've found so far is if this is the region I'm interested in, and we're trying to find the center of mass, right? There's two different points. There's the x bar location, but there's also the y bar location. How do we find the y bar location? Well, if I'm trying to find the y bar location, so similarly, I want to go through the whole process. But a good way to think about it is, where is the center of mass going to be of all of these pieces in the y direction? So let me draw my picture again. So here's my curve. Here's my A and my B. What if I wanted to find the center of mass of just like this one slice right here? Well, it would be right dead center. So if this is some xi, this height is going to be exactly, so if this is y equals f of x, here's my y-axis and my x-axis, where is this point going to be, my y bar height for that one little piece? It's going to be exactly half the height of the bar. But what's the height of the bar? F of x. So in this case, it's going to be half of the f of x sub I. That's going to be what the height is of that particular point there. And we wind up basically averaging a bunch of these out together. So you can think of it as basically we're wanting to do these all, because now we're the distance we're interested in is going to be with respect to the x-axis when we're trying to find the y center of mass, right? The y center of mass is how far from the x-axis is everything. And we'll wind up with a formula that looks like this. So y bar equals, similarly, 1 over a. We've got our integral. We're integrating over the same region as before. But now the distance, instead of having x here, x was the distance in our picture. So just at a given point, x is the distance from the y-axis of the thing that we're looking for, of our center of mass. Over here, what is the y coordinate? It's half the total height of this thing. So it's not going to be x anymore, it's going to be half of f of x. And then we still have the total area to take into account. So this piece right here is replacing, it's just the distance, it's replacing x. We still have the rest of the equation, f of x dx. So this part is just replacing this x here because it's just a distance. What is this distance, d? Whereas similarly over here, we were interested in what is this distance, d. Over here, the distance d is just whatever the x-coordinate is of the given point that you're interested in. Over here, the distance d is the distance, half the distance from the x-axis up to the total height of the curve. That's the middle part of this particular slice that we're looking at. So, keeping that in mind, we can simplify this to y bar equals 1 over a times the integral from a to b of 1/2 f of x squared, because it shows up twice, dx. And this formula gets a little uglier if you do have a lower bound that isn't the x-axis. If it's a g of x like this, right, it's going to be the midway point between these two curves, and you'll wind up basically having to average these. So you'll have f of x plus g of x divided by 2 to give you the value that you're looking for here. And then the total area will be the f of x minus g of x, and you'll basically have an f of x plus g of x and f of x minus g of x, and you'll multiply them together and you'll get an f squared minus a g squared term, but also with this factor of 1/2 sitting out there. So you can do this with the second curve, but again, I'm not going to make you do that. If you want to look them up, they're in the book. This whole piece, again, is referred to as the moment with respect to the x-axis. It has to do with how far everything is from the x-axis instead of from the y-axis. So these are the two formulas that we need to know. This one here and this one here. So let's do a quick example. And again, these two formulas only work for regions where the lower bound of that region is the x-axis. There is a different formula if you have a different lower bound. You'll have to look in the book if you want to do any of those, but I'm not going to assign any of those. So let's say I want to find, here's my region, x, y, and I want to say it's maybe just like a quarter circle of radius 2. So this is the region that I'm interested in, only in the first quadrant here. So find centroid of the shaded region, with the assumption that that region has uniform density. So if you had to ballpark it, where would it be? I would say it's going to be, right, if it was a perfect square, it would be dead center, right? It'd be at the point 1, 1. But it's not a perfect square. We're missing this region over here. And that tells me that this point is too close to the edge because we're missing some stuff that isn't going to balance it. So I'm expecting it to shift in this way a little bit. One thing that I do notice based on this, let me remove that. So what I really expect is the point to be maybe something like here-ish. But I do know that because of the symmetry of the shape itself, I don't need to find both x bar and y bar. X bar and y bar, these two coordinates, should be the same. So notice x bar should be equal to y bar by symmetry. So I should only have to find one. Because of the shape, I'm expecting it to basically be on the line y equals x. That's what I'm suggesting here. So once you've found one, we know what the other one is. Okay, so using that symmetry, we just need to find one of these. And so let's pick which formula looks easier. I'm guessing that this formula is going to be easier. I'd rather deal with x than with f of x. Okay, so let's try to use, so let's find x bar, which is equal to, again, 1 over a times the integral from a to b of x f of x dx. So I need to find the bounds a and b, I need to find the area, I need to figure out what f of x is for this thing. So we need all of these things. We need A, B, capital A, the area, and f of x. A and B are easy enough. When I integrate this region, I need to integrate between 0 and 2. So A and B are 0 and 2. Capital A is similarly easy. Normally we would have to do an integral, but in this case, because it's a section of a circle, I can just use geometric formulas. So for the area, I know it's a quarter of a circle. In this case, it's going to be 1/4 of the area of a circle, pi r squared. But what is our radius for this particular circle? The radius is 2. So for us, that's equal to 1/4 pi times 2 squared. 2 squared is going to be 4. It's going to cancel with this. The area of that region is pi. And f of x, this piece, we know the area of a circle is x squared plus y squared equals the radius squared. In this case, that's going to be 4. As we just saw, the radius is 2. But I need to write this as f of x. We need to solve for y as a function of x. And so to do that, I will do y squared is equal to 4 minus x squared. So I'll subtract x squared from both sides to separate the x and the y. And then we'll get rid of the square with the square root. We've got plus and minus the square root of 4 minus x squared. But for us, the portion of the circle that we're interested in is up in the first quadrant. I'm interested in only the positive portion of this. The positive square root will give me the whole top half of the circle, so the top semicircle, and the negative sign will account for the bottom of a semicircle. But since the region we're interested in is only in the top, we want to pick the positive version. And so this is my f of x. My f of x is going to be equal to the square root of 4 minus x squared. And so if we put this all together, we get that the x bar, the center of mass, the x coordinate for our center of mass, is going to be 1 over the area, but we just said the area was pi, times the integral from 0 to 2, from a to b, which is 0 to 2, of x times f of x. X times f of x, which is 4 minus x squared dx. And so this integral will give us the center of mass that we're looking for, at least the x-coordinate of the center of mass. How do I solve or evaluate this integral? Luckily, we have this x hanging out over here, and everything inside the square root is a 4 minus x squared. It involves an x squared term. So I have something in here that's a quadratic. I have a linear term outside that can be proportional to the derivative of this quadratic, and so we can do a u substitution on this. If this x wasn't here, we'd be having to do a trig substitution, but because of this x, I can do this as a u substitution. So I can let u be equal to 4 minus x squared, and that tells me that du will be equal to negative 2x dx. And let's change the bounds of integration as well. So when x equals 0, what is u equal to? And then again, when x is equal to 2, what is u equal to? So I can convert the bounds of integration from being in terms of x to being in terms of our new variable u in just a minute. So when x is 0, I plug in 0 here, and I get that u must be equal to 4. And when x is equal to 2, I plug a 2 here. I'll get 4 minus 2 squared, so 4 minus 4, which is 0. So I'll get 0 in this case. I almost have everything I need. I have my x dx, but I really want a negative 2 x dx. So let me put that negative 2 artificially in there. And then I'll account for it by putting another negative 2 in the denominator out in front of everything. So this negative 2 in the denominator will cancel with this negative 2 that's in the numerator. And we wind up with, when it's all said and done here, I'm going to get 1 over negative 2 pi. Just put the negative sign up in front. The bounds of integration, the lower bound 0 became 4. The upper bound, which was 2, became 0. And I've got negative 2x dx, that's my du, and then I have the square root of 4 minus x squared, that's the square root of u, and I have my du. I'm going to change the bounds of integration here because it's weird to have the large number on the bottom and the small number on the top. And whenever we do that, all we're doing, so we're basically right now you could think of it as we're integrating from 4 down to 0, and we're doing it in little increments that go this way. This is like my little increment dx, but we're really doing it in increments of negative dx because we're decreasing each time. So instead, I want to integrate in this direction with a bunch of little positive dx's. So when we go from 0 to 4 with positive dx's, that's the same as going from 4 to 0 with all these negative dx's, and it indicates that there's a sign change that occurs. That's the standard thing that you've hopefully seen or familiar with. When we change the bounds or swap the bounds of integration, it'll flip the sign of the whole thing. So I'm going to have 1 over 2 pi times the integral from 0 to 4. By flipping these and introduce a negative sign, and that negative sign canceled with this negative sign that we used to have sitting out in front. Now I'm going to do that integration. Square root of u is the same as u to the 1/2 power. When we integrate that, the power will go up by 1, so from 1/2 up to 3/2. And to make up for that 3/2, I need a factor of 2/3 in front of it. We're evaluating between 0 and 4. And so I'll be able to cancel this 2 and this 2. I'll have 1 over 3 pi. And then I'm going to plug in 4 to the 3/2 minus 0 to the 3/2. 4 to the 3/2, so the 0 to the 3/2 isn't going to contribute anything, but this 4 to the 3/2, let's take the half part first. So take the square root first, I'll get 2, and we'll be left with 2 cubed, which is 8. So this whole thing is just 8, and we get 8 over 3 pi. And if we plug that into a calculator to get a decimal approximation, let me do that real quick. I wound up with about, right, so go back to our original problem. Our intuition was it's going to be right about here-ish. We said if it was all the way at 1, that was too far. That was too big of a number. So it should be a little bit less than 1, but still pretty close to 1. And when I plug this in, I get about 0.84, which makes a lot of sense. So at this point, let me just actually, before I say that 0.84, that's what I'm vaguely remembering. Let me make sure that I get actually 0.84. Here's my darn calculator. There we go. Closer to 0.85. It's like 0.849. Rounded to 3 decimals, so I don't have to erase. But sure enough, a little bit less than 1. And then again by symmetry, so putting it all together, the centroid occurs at the point x bar comma y bar, which is going to be approximately equal to the point 0.849 comma 0.849. By symmetry, we were arguing that the x and y coordinates should both be the same because of the symmetry of the shape. And so sure enough, we've got an answer that makes some sense. It matches our intuition. This is how you can find the center of mass. So hopefully these 2 applications make sense. There are other applications. I'm not going to focus on many of them. You will see them more and more if you take some physics classes, which most of you are engineers. You'll have to take physics classes anyways. You will see some of these other applications. Let's call this good for today.